The next talk is a recorded talk towards generic higher order unification implementations in Haskell by Nikolai Kudasov.
And together with my collaborators, hello everyone, my name is Nikolai Kudasov, and together with my collaborators Artem Starikov, Fedor Ivanov, and Damir Alfiatonov, we will present our work in progress on an approach to generic high-order unification implementations in Haskell. High-order unification is a process of solving symbolic equations with functional variables, and it is widely used in type checkers, interactive proof assistants, and high-order logic languages. As a simple example of its use in a dependent type checker, consider an identity type for two pairs. Now, since the identity type in Martin-Love type theory is well formed, while types on both of both pairs is the same, we have to check or infer and unify the types on both sides. In the case of dependent pairs, we will need to infer the type family, unless specified, that indicates the way that the type of the second component depends on the value of the first component in a pair. This can be reduced to a simple system of unification constraints, as you can see on the slide, to be solved by a high-order unification algorithm. Now, in the past 50 years, a multitude of high-order unification algorithms has been accumulated both in the literature and in various implementations. Huet's preunification algorithm and Jensen and Pietrkowski's full high-order unification algorithms are perhaps the first and most well-known. Miller's high-order pattern unification limits the kind of unification problems that we're trying to solve to a decidable and unitary fragment that can be processed efficiently. For these reasons, variations of Miller's pattern unification is very popular, specifically in type checkers, including interactive proof assistants based on dependent type theories. Now, automated theorem provers, such as, for example, zipperposition, often require full high-order unification. And particularly, one of the recent papers by the team behind the zipperposition presents a combination of techniques dubbed full efficient high-order unification that makes this very efficient. That said, reusing these implementations is not really straightforward. The algorithms in the literature are often stated for a simply typed lambda calculus or a similarly minimal language, and implementations are often bound to a particular language or core language or a tool. To the best of our knowledge, none of the high-order unification algorithms are available as a library implementation that are ready to be reused by a developer of a new formal system. Now, this unfortunately forces developers of new tools or new formal systems to either learn and implement complicated higher order unification algorithms and also adapt them to their own language, or abandon user-friendly features in their tools, such as implicit arguments or type inference in their proof assistants.
One of the main inspirations for our project are generic libraries for first-order unification. In particular, the unification of the package implements such a library which follows Tim Short's functional power. In this library, syntax of terms is generated from a signature. It is a non-recursive data type which specifies possible syntactic constructions of the object language. Terms in this object language can then be recovered by taking a fixed point of the signature. Syntax for unification terms is generated similarly by injecting unification variables into the object language. Unification is then implemented in a generic function, parameterizing over the signature. Now, we would like to generalize this approach to higher order unification. To do that, we need to figure out how to freely generate syntax with binders, and also how to account for semantic equivalence of terms. Setting aside implementation details for a moment, we rely on second-order abstract syntax. Just like generic unification terms, second-order abstract syntax is generated freely from signature. In this case, however, the signature also accounts for the binders. Each subterm of a syntactic construction is allowed to bind 0 or more variables. For example, function applications takes 2 subterms, both without binders. At the same time, lambda abstractions take 1 subterm, but with a single variable binder. Second-order abstract syntax also freely adds variables, but they are local and we do not normally consider them as unification variables. So we inject, in addition, second-order variables or metavariables. They are always parameterized with a list of terms. Metavariable substitution may only use these parameters to replace the metavariable. Although they may behave like functional variables, they cannot take other metavariables as inputs, and thus they are not higher order. Equipping second-order abstract syntax with equational logic, we get second-order equational logic, which we believe is a great framework to do higher-order unification in. Unlike higher-order abstract syntax, for example, second-order abstract syntax is much easier to work with. We also know that higher-order unification can be considered as a special case of equational unification for second-order abstract syntax, since equational theory of higher-order systems can be presented as a set of second-order equations. Parameterized metavariables also partially cover functional metavariables. And finally, we know how to present second-order abstract syntax in Haskell and mix it with the data types carte approach. Now, to make things actually work, we need to select appropriate representation of syntax binders and somehow adapt known higher-order unification algorithms to the second-order setting.
There are many possible ways to implement abstract syntax with binders. And here you can see a non-exhaustive list of representations. In our project, we want a representation that provides some kind of intrinsic scoping, efficiency, and compatibility with data type carte approach, or similar. At the moment, we are working with the free-foil approach, which is essentially a version of free monods with binders. Free-foil allows us to generate an efficient, intrinsically scoped abstract syntax with binders. Here, signature is given by data type with 2 type parameters. The scope parameter corresponds to subterms with exactly 1 binder, like body of a lambda abstraction or let binding. The term parameter corresponds to plain subterms, like the 2 subterms of a function application or the first subterm of a let binding. The type constructor AC is provided by the library and is akin to the fixed point combinator that automatically adds variables and binders in the correct places. The phantom type parameter n is statically tracking the scope of a term. This is a feature of an underlying foil approach, which is in turn a type safety mechanism on top of the wrapper, an efficient implementation of the barn-direct convention for bound variables, which is used by Glasgow Haskell compiler as well as Agda. Finally, The library implementation of FreeFoil provides convenient template Haskell helpers that work well with parser generators like BNF converter, making it easy to develop prototypes for small object languages. To recover second-order abstract syntax, we need also to add parametrized metavariables. Instead of having them built in, currently we choose to rely on compatibility with data types carte approach and specify a separate signature for metavariables. The second-order abstract syntax is then generated freely from the sum of object language signature and metavariable signature.
So before moving on to higher order unification, we consider a much simpler problem of second order matching. Matching refers to a subset of unification problems where unification variables or metavariables are located only on one side of each unification constraint. Since in our setting metavariables are parametrized, matching is much more interesting than its first order counterpart. Second order matching is not unitary and it may produce multiple distinct solutions. It also partially covers higher order unification and is useful in comparison of substitutions, but also requires some non-trivial techniques for an efficient implementation. Interestingly, second order matching does not require fresh metavariable generation in our implementation. And we are at the beginning of our journey, and so far our main results are an implementation of the second order matching via FreeFoil and a preliminary test specification for untyped higher order unification problems. We are also working on generalizations of Huet-style preunification and function as constructors higher order pattern unification. However, both require a proper generalization of hereditary substitution, and the former also requires some generalization of Huet-style projections. Talking about our future work, first, we plan to implement a higher order unification benchmark suite to compare unification algorithms in isolation rather than as a part of type checker or a theorem prover. This is somewhat a tangent goal, but we think it may be useful to a larger community. Second, we plan to implement at least a generalization of some basic unification algorithms, specifically Huet preunification and Libel and Miller generalization to pattern unification, called functions as constructors higher order pattern unification. Third, we would also like to implement a somewhat useful application that would rely on our generic algorithms. For example, we think every implementation of talk may be interesting. And finally, there are, of course, many places for improvement and configuration, especially with respect to the performance of our generic implementation. In particular metavariable representations, more precise control over laziness in Haskell, optimization techniques such as interning or fingerprint indexing should all be considered as potential improvements, of course, after we have a fully working prototype. And this is basically it. Thank you all for tuning in, and we will now be open for questions or comments on our work.
Okay. Great. Nikolai, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, perfect. Great. Other questions for the speakers? Okay, then let me start with one. So, yeah, you said the the goal was to, of course, make it easier to bootstrap new languages, experiments perhaps as well. Also some toy language that you mentioned in the end. Yeah. So what do you think about scalability? Do you want to focus on these simpler applications, or do you see this also scale to arbitrarily complex compilers?
Thank you for the question. I think that at the current pace, at least, we're looking forward more into small systems and just being able to reproduce results and algorithms from papers and stuff like that. One maybe important block towards better scalability is the ability to work with the mutually recursive definitions. And I think that's the main one, I guess. And the only system that addresses that in some way that I've seen is hypertypes, but that's a slightly different approach, I guess, than what we are taking at the moment. So for now, we're choosing sort of to stick with the somewhat simpler free FOIL approach. Hopefully, we'll figure out how to make this truly scalable. But for now, we're looking mostly at fast prototyping, maybe, rather than developing large-scale systems.
Makes sense. Thanks. Other questions? Okay. Otherwise, let's thank the speakers again.